Hello, this is Sachin Patil. Today I am going to Hello, this is Sachin Patil. In this video, I am going to explain Introduction to Embedded Systems Shibu KVs, chapter number 10, part 2 video. Real-time operating system based embedded system design. So already I have covered first two topics, subtopics, which are operating system basics and types of operating system in part 1 video. In this part 2 video, I am going to explain task, processes and threads. Task, process and threads. What do you mean by task? The question arises, what are these task, process and thread? We'll see one by one. Task is defined as a program in execution or operating system context. The task is defined as a program in execution, and the related information is maintained by the operating system for program. So in simple word, I will try to explain what do you mean by task. Suppose it's a job or work, right? What has to be done by the any embedded system like this mouse. So mouse, what is the work of this mouse? The mouse will move and we move the cursor, the cursor will move on the screen. It's the work. And for this embedded system is implemented, or we can say designed. So for that they have used this sensor, then buttons, and memory is inside, and it is powered by the microcontroller. So to implement this mouse, they created the three tasks. One task for suppose. So if you don't want to make use of this operating system help, then these components what are used connected to microcontroller are programmed in sequence. So if you keep that all the programs in one sequence, one while one in super loop, they execute one after the other, but that is not required in embedded systems. Some real-time systems, embedded systems, operating system need to be used. So in this, if the operating system is used, it will do the 2-3 different works. What is the job it will do? It will sense through the sensor, and the program which is stored in the memory, it executes, and it will identify where a location of the mouse. Based on the movement of the mouse, the cursor will move on the screen, and we'll use this button for different options. Okay. For this can be implemented for these all jobs either in one program only. We write for every different devices, peripheral devices connected to the microcontroller inside, or we write the same programs in separately, right? And that we call it as a task. Not separate program we'll write, within the same main program only we write a sub programs that we call it as a task or job or a process. And task and process are interconvertible. interchangeable, means most often in an operating system context they are interchangeable and they are used for each other, and the process requires various system resources, the task or a process whatever. To execute that, it needs a system resources. The most important system resource in any embedded system is CPU, central process unit, or ALU, arithmetic logical unit, what it has, processor time, finally. Executing the tasks, memory for storing, and the code corresponding to the processes and associated with variable IO devices for information actions are required. But most important one is among all these is CPU time. Next, so what is, you can say, task? So for this a system, embedded system, which is monitored by a mobile, or these will monitor or on off condition we control by of the fan, air conditioner, humidifiers, dehumidifiers, and through the sensor will take the input, and based on that will the actuators will give the input to this to operate. Okay. As a whole, this embedded system will is designed to control all these, but individually if we can write the program to these all devices to be controlled by this. So for that we created tasks, right? So task, when you create the separate stack data and memory is allocated to that. So when you use the operating system, then one sample program I will show you that which is written for VxWorks operating system. It's a real-time operating system. So within the, look at here, we write the within a main program only, the two tasks are created with the key. Look at here, task spawn, where I'm moving the mouse cursor, where I'm pointing the cursor. It is created by the task name, its priority, how much stack size is required, and all other different parameters. And then that whatever the task program is there, you have to write void task 1 and the related program we have to write. Like that for task 2, task 3. And based on the priority, these tasks are executed. So here there are various key functions, built-in functions are used. These functions are called as nothing but as system calls. This is system calls, means the operating system will provide these commands to invoke, get the service of the operating system. So where creating a task or a process and then writing the code and then executing it. It depends. So instead of writing one single program for any embedded system, we'll divide that program based on the different jobs what that done by the embedded system. For example, mouse, I told you, and then that divide into small chunks the same program and we execute. The same program is written within the task. So here you can see here this within the task we write the same program for sensor of the mouse, program for keypad, program for memory operations. So like that you can create that task and these are executed based on the priority. Here the priorities are mentioned, and along at the same time these are the commands for system calls and the operating system services to extract. And why we, instead of writing one single program for the mouse, why have to create in a tasks? So when you create in a tasks, right, the CPU is more efficiently utilized, and the operating system will provide a platform to all these tasks to execute their programs on CPU. Because of this, the response time or throughput will increase. So here, the tasks which are created, we can assign the priority, and based on the priority we can do the work. Otherwise, if you write one stretch the program, but is despite of priority, that all the programs, task programs or code is executed in a one single sequence. But if you write in small tasks, based on the priorities, the related program, for example sensor program or keypad programs, based on the need they are executed, right? Even the operating system will provide the facility to change the priority also in between. Okay, this is a task. I told you that task 1, task 2, 3, like that tasks are created. And how the these tasks they execute their code on CPU is based depend it is helped by the operating system. So how operating system help the tasks to execute their code on the CPU is it it properly schedules, that is called as a scheduler, resource allocates. Which is the important resource? CPU. So you can see here this CPU. CPU is the important resource of any embedded system, and its CPU time is very precious. It has to be allocated to all the different tasks. Who is allocate? The operating system will allocate, and then based on that allocated time, these tasks execute their codes. Structure of process, structure of task or process. The the process leads to a concurrent execution. You feel that these are all executed concurrently, but simultaneously on CPU. But these tasks are not executed simultaneously. Only one time the CPU can handle or execute its program of a single task. I mean, how can you feel that? So, if suppose task 1 has a code or a program of 20 second, and task 2 has a 30 second, task 3 has 60 second, then the time allotted by this every time is 10 second, means the task 1 completes only 10 second of its code execution, and remaining 10 second after the execution of 10 second of all these it executes. If it's a round robin, fixed amount of time is given to every task, and then after that, when the task 1 turn comes, at that time it again executes the remaining 10 second of its code. So one simple example what I have given. So like that. So the process leads to a concurrent execution of the task, thereby the efficient utilization of the CPU and other system resources. The concurrent execution is achieved through the sharing of CPU among the processes. That's now what I explained. And this process mimics the processor in properties, holding the set of registers and process status and the program counter, all such things. When the process is created or a task is created, it is allocated stack, register, status register, and a program counter is also accessible to it. And the memory organization of the processes. When a process is get created, the memory allocated to every process or a task is segregated into 3 sections. One is a stack memory, data memory, and code memory. The stack memory holds the temporary data or any intermediate results are generated push to stack. And the data memory holds all global data or the processes. The code the code which is related to the that particular task. For example, here the three tasks what I have mentioned. One is sensor program for that we write a piece of code that we in task 1, and button related program for button operation, that the program what we write in task 2, like that. The code is stored on the code memory for the related task. On loading a process into the main memory, a specific area of memory is allocated for the process. The process state and state transition. Next thing what we are learning on in here. So here the creation of the process to its termination is not a single step operation. The process traverses through the series of states during its transition from newly created state to terminated state. For example, it's this creation to termination, whatever the different states it acquires is called as a process life cycle. For example, here look at here, we'll take the same example what previously we discussed. Once the task is get created, right, and this at the same time task 2 is also is created, right. So once these tasks are created, they created in a ready, all the resources are available. For example, receive memory, IOs, input output devices, and all any other resources required. So these all are available, only it is waiting for CPU time. And when it gets the CPU time, right, from the by the operating system, it is assessed, the same task will goes into running state. So here when this task 1 is executing its code, task 2 is in ready state because it is already acquired. It may be priority 1, task 1. So task 2 will wait for it to finish, and then when task 2 get the chance, it comes into running state. It will run that. At the time task 1 is suspended, or even if completely finished its code execution, and then it goes into blocked or completed states. So task 1 is created, it comes into ready state. When ready state, only for CPU it is waiting. When it gets the CPU time, it goes into running state, it start executing its code. When it completely finishes the execution of the code, it goes into that task goes into completed state. If in between any other task, a higher priority task invokes, then preempt, then it goes into block state. And when it gets back the resource which is acquired by the higher priority task, then it comes into ready state, then into running, and it finishes its task 2 will also finish the code. So these many different states acquired by the they are explained in this next slide. What do you mean by create state? The state at which the process is being created is referred as a create state. The operating system recognizes the process in the create state first. Okay? And ready, the ready where the process is inserted into the memory and waiting for the processor time to execute. I told you, right, waiting for only processor time. It's called the ready state. Running, the state where the source code instructions corresponding to the process is being executed is called as a running state. Next is a block where the running process is temporarily suspended. Just I told you, right, if any higher priority task resumes, and then the lower priority task which is running, it gets suspended. That is called the suspend, means the resource is taken back and then it is allocated a higher priority task. so suspended for execution and does not have immediate access to the resources. A completed state where the process completes its execution. Thread is nothing but a small chunk of the code. The thread is a primitive that can be execute code. A thread is also known as a lightweight process. So this process or a task, what you just try to explain, we have to refer this code. So if task 1, task 2, these are also called as a process. I told you at the beginning only job, task and process are interchangeable. One and the same task, when it is created, it's also called as a task. When it is executing task, executing task is called as also sometimes process. Okay, this task, if it is a very large task, we divide again this task into this code into small chunks. Those small chunks are called as threads. So if are called as threads. Just a moment. Okay, different thread which are a part of the process. I told you share the same address space, memory and data memory and code memory. I told you when the task is get created, memory, some space is reserved, memory space, where that memory space which is reserved for that particular task in the main memory, they are subdivided again into stack memory, data memory and code memory. If the task 1 again subdivided the whole program into threads, I told you thread 1, thread 2, thread 3 like that. So then the memory which is allocated for task 1, within the same memory, again this stack memory is divided into thread 1 memory, thread stack memory, thread 3 stack memory like that. So here they have mentioned stack memory for thread 1 stack, right? This gives a clear idea about that. So here one simple example what they have given here. The stack memory is shared by the thread and the same time data and code memory also shared by the thread. Thread is nothing but a part of a code task. Okay. Concept of multi-threading. So what is the advantage of this? If you want the threading, better memory utilization. So how come better memory utilization? Multiple threads of the same process share the address space, data space and also it reduces the complexity of inter-threading thread communication. Since the process is split into different threads, when one thread enters the wait state, the CPU can be utilized by another thread of the process. Do not require the event. Efficient CPU utilization. CPU is engaged all the time. So there is thread standards. To write this standard or management, some standard is set. That standard, one of the common available threads class libraries is a POSIX, Portable Operating System thread standards. So and the threads is also written in C language only. And again we have to write how the task spawn is used to create the tasks like that. Within the task, if you want to create a thread, again some system calls are there. The POSIX standard system calls interface, that we have to use some commands to this. So there are two types of threads: user level thread and system level thread. User level thread means for our convenience the process or a task one is divided into thread 1, thread 2, thread 4. But the operating system, if it is a user level thread, the operating system will look at all these threads as one single thread or a single process. It cannot, I give the identify this thread 1, thread 2, thread 3 separate entity. It assumes that it's a single entity and it will execute, right? But in a kernel system level thread, the operating system will identify or recognize each thread what is created within the task. So look at here, a single task, task 1. Within that, the task 1's again program is subdivided in the smaller chunks called as a thread 1, thread 2, thread 4. So how this task 1, after that task 2, based on the priority, they make use of the CPU time and execute their code like that. Within the task, whatever the CPU time is allotted, again it is executing, right, utilized by these threads to execute the piece of code. The kernel level thread are individual units of the execution which the operating system treats as separate threads. If it is an operating system, kernel level threads, if your units are executed. The execution switching of or context switching of user level thread happens only when the currently executing user level thread is voluntarily blocked, and involves a lot of kernel overheads and involves system calls for context switching. So thread models, there are three models: many to one model, one to one model, or many to many model. So many to one model means many user level threads are mapped to the single kernel. It's called as a many to one model. One to one model means each user level thread is bound to the kernel, and many to one means in uh, in this model many user level threads are allowed to be mapped to the many kernel threads. So these are the examples what they are given. It's on screen, so you will get a good knowledge of this, right? Task, process, and threads in this I have explained very clearly. If you have any doubts, you can send a mail. I will send a reply to that. Okay. So thank you for watching. Please like, press the like button, and then subscribe for further updates. Thank you.